My people, the next two are going to be rather straightforward, except, I mean, they're going to be sort of graphs that you're not familiar with. This one, I basically took x squared plus y squared is equal to 16, and then I added a trig function to sort of make it wavy, just because that makes it a little more fun. It also makes it a little less predictable in terms of this kind of stuff. I want to find the equation of the tangent line where x is equal to 0, meaning here and here. Okay, well, let's go ahead and get started. I need to take the derivative, that's 2x plus, well, this one right here should be actually relatively straightforward too. It's going to be 2 cosine 3x times 3, so 6 cosine of 3x plus 2y, y prime is equal to 0. Now, as is the case, often we can go ahead and cancel. So that 2 and that 2 go bye-bye. The 2 from the 6 goes bye-bye and leaves me with a 3. And I'm left with, and I'm going to go ahead and shove these over to the other side because this is the only one with a y prime. So y prime is equal to negative x plus 3 cosine 3x. And therefore y prime is equal to negative x plus 3 cosine 3x all over y. Now, when we can actually find, we need x and y, but we can find the order pair easy enough. So this is my derivative. If I go ahead and plug in 0, I'm going to get 0 squared plus 2 times sine of 0 plus y squared is equal to 16. Well, that's 0, so y is equal to plus or minus 4. My order pairs are 0, 4, and 0, negative 4. That should not come as a surprise. You can eyeball it from the graph. Now we need to take both of these and plug them in over here. Now when we do that, we get y prime of 0, 4. We're going to get negative 0 plus 3 cosine of 0. Now be careful, cosine of 0 is not 0 over 4, and that winds up being negative 3/4. Well, that means that I have y minus 4 is equal to negative 3/4 x minus 0. Okay, and here at 0, 4, that looks like a negative slope, so that's reasonable. Let's go ahead and do the y prime for 0, negative 4, and we're left with, of course, the same numerator, just a negative denominator, which gives us positive 3/4, and so I have y plus 4 is equal to positive 3/4 x minus 0. Now, let's go ahead and I tell you what, we haven't looked at a graph in a little while. Let's go ahead and do that. Let's go ahead and get rid of these. Let me get it within our window. Let's get rid of all these that we have over here, and let's get ourselves a new equation. So we have x squared plus 2 sine of 3x, okay, plus y squared is equal to 16. Okay. Now, of course, you can't see it because we need to zoom out a little bit. Okay. Now, if to basically show that these are indeed our tangent lines, or at least that it's reasonable based upon what we see, we need to basically plug in the equation line, the two equations of the tangent line. And so our first one was y minus 4 is equal to negative 3/4 times x minus 0. Boom. And we see that that one looks reasonable. Let's go ahead and look at a new equation here as well. We have x plus 4 is equal to 3/4 x minus 0. Of course, I could have simplified those into slope-intercept form, but I'm not really caring about that right now. And we see that we have that reasonableness right here. We see the fact that it does look like it comes down and hits at that very point. It has the same, it seems reasonable that it has the same slope of the curve at the point of tangency. And the same thing with this positive 1 down here. Okay. Now, let's go ahead and do our next example. And this one's going to be a short video because I probably want to, the bear of a problem that I want to get to is probably going to take a little bit longer. So this one right here, again, something that I was just playing around with the grapher. I just wanted something fun and that we hadn't seen before. Now this obviously has 3 pieces of the graph, but what I'm really looking for is the point right here at 2, 2. So let's go ahead. We can do this by a product rule, but that means it's 3 factors, right? So it's probably a better idea to distribute that xy, and I get x squared y and xy squared is equal to 16. Now that's a little bit easier to deal with because I'm not dealing, I have to do, it's just kind of pick your poison. I mean, do you want to do the product rule twice with 2 factors or once with 3 factors? So let's go ahead and do this one right here. We have the first times the derivative of the second plus the derivative of the first times the second. There's the product rule for that first term right there. And then we're going to do it again. First times the derivative of the second plus the derivative of the first times the second, being careful, of course, that the derivative of a constant, that 16, is 0. Now, I can clean up, but I also need to recognize the fact that these are the 2 terms that have my y prime, okay? But, again, do I actually need to solve for y prime, or can I just go ahead and plug in the 2, 2 right now? Now, I do want to clean it up. I mean, remember that the reason why I have all this notation is so that I can remember, brackets here, I do that. So I took the derivative here, brackets, brackets. But, I mean, this can be written with a whole lot less notation. Now, if I want to plug in 2, 2, I simply get 2 squared times y prime plus 2 times 2 times 2 plus 2 times 2 times 2 times y prime plus 2 squared, okay, is equal to 0. This winds up being 4y prime plus 8 y prime plus 4 is equal to 0. So that winds up being 12y prime is equal to negative 12, so y prime is equal to negative 1. Now just eyeballing that shouldn't really surprise us, okay? And so what we have here is we have y minus 2 is equal to negative 1x minus 2, and there you go. Now, if you actually notice, and we'll just talk about this just for a second, if you actually notice, if you turn this graph that way, you notice that it does have a symmetry to it. It has a symmetry right about the identity function right here. And that means that it is its own inverse. Well, when you look right here, that shouldn't be too surprising, because when we take an inverse, like when we do it analytically with notation, we swap x and y. Well, if we were to swap x and y in this equation, we would get yx, y plus x is equal to 16, which is, of course, identical to the original. So, it shouldn't surprise me that I get that well, we'll talk more about symmetry another time. On second thought, I'm going to go ahead and I'm going to get to the next problem, largely because I just don't want to press stop, actually. So, sketch the circles, okay? Y squared plus x squared is equal to 1, and y squared is equal to x minus 3 plus x minus 3 squared is equal to 4, okay? So that's 2 circles. This one is at the origin. This one is centered at 3, 0. So stop for a second and see if you can actually imagine what those look like, before I spoil the surprise and show you here. There is a line with positive slope that is tangent to both circles. Determine the points at which this tangent line touches each circle. Okay. Well, I went ahead and drew it out for you. Okay. So that's basically what it looks like. This, of course, right here is the, x squared plus y squared is equal to 1. And this right here is the x minus 3 squared plus y squared is equal to 4. Now, it touches here, it touches here, and I need to know what the equation of that line is. Well, the problem is that you obviously, in order to figure out the slope of that line, you need to figure out you need to try and figure out two different ways, perhaps, to represent the slope so that you can set them equal to each other and solve, okay? Now, what happens here is that if you try to use, the derivative, the derivative of this one or the derivative of that one in terms of a formula, you get something like this. Okay, so let's back up. And let's say that I want to find the derivative of both of these. And basically I get 2y, y prime, plus 2x is equal to 0. Now I've done circles before, and so it winds up being negative x over y. So there, right there, is the derivative of that first circle right here. The derivative of the second one is 2y, y prime, plus 2 x minus 3 is equal to 0. Of course, the 2's again cross out. And I'm left with y prime is equal to 3 minus x over y. So I just, instead of making negative x minus 3, I just use the negative to flip the difference. Now, you might think, well, gosh, why don't I go ahead and set those equal to each other? Okay, well, let me show you what happens when you do. You get negative x over y is equal to 3 minus x over y, and you get negative xy is equal to 3y minus xy, and therefore you get 3y is equal to 0, or y is equal to 0. Y is equal to 0 is, the x-axis. So obviously, that doesn't really get us anywhere. That's kind of a false start. The problem with this is that it cannot, actually it probably can be done, but most efficiently it's not done. Most efficiently it's done with a little bit of rudimentary geometry. Now, if the tangent line hits here and here, then the slope of this circle here and the slope of the larger circle here are equal, right? Because, the curve has the same slope as the tangent line at the point of tangency. Well, if it's tangent line, if both of those points have a tangent line that have the same slope, then they also have a normal line that is the same slope. And a normal line of a circle necessarily goes through the origin, because the normal line and the tangent line are, of course, perpendicular by definition, right? So what that means is this right here is a right angle, this right here is a right angle, and if you look at that for a moment, you'll recognize the fact that what I have now is similar triangles. I have similar right triangles with this one, okay, this one right here being embedded within, let's see, we'll do it green, being embedded within this larger triangle, right? So if they're similar right triangles, remember that means that their sides are proportional. And if their sides are proportional, I already know two of the sides. I know, because this has to be a radius, because it goes from the edge of the circle through the center, that this is 1. I also know that this is 2. So every single side of this smaller triangle is half of the larger triangle. Well, here's why that's going to benefit me. This right here is 3. If that's 3, then this point right here, it doesn't just look like it goes through the point -3, 0. It does. That right there is the ordered pair -3, 0. Now, because that's the case, I can now actually get a second representation of the slope. Because this point right here is a point on this circle. Well, it's also a point on the top half of the circle. And the top half, or the top semicircle, okay, is y is equal to the square root of 1 minus x squared. And therefore, every point on that top curve has the form x root 1 minus x squared. So, if that's the case, this point right here can be represented like that, and I get x root 1 minus x squared. That means that the slope between those 2 points can be written as, well, let's y2 minus y1 over x2 minus x1, or just the square root of 1 minus x squared over x plus 3. Okay, well that's kind of convenient, because now that I can set equal to one of these. So I know that this circle right here has a derivative of -x over y. And I can set that equal to the square root of 1 minus x squared over x plus 3. But I still have a problem. I still have this y right here. Well, that's really not a problem, because I've already talked about the fact that I'm dealing with the top half of that, and therefore x squared plus y squared is equal to 1. In this case, since we're dealing with the top half, the top semicircle, is synonymous with y is equal to the square root of 1 minus x squared. So what I have is -x over the square root of 1 minus x squared, and now that is a proportion that I can solve. And I get -x squared minus 3x is equal to 1 minus x squared. The -x squareds go bye-bye, and x is equal to -1/3. Now, all that is saying is this point right here has an x-coordinate of -1/3. That's what it's saying. But if I know that if it has an x-coordinate of -1/3, then it's very, very easy to get the corresponding y-coordinate, 1 minus 1/9, and that becomes basically the square root of 8/9, or the square root of 8 over 3. So the ordered pair that I had, okay, is basically, this means that the ordered pair is -1/3 root 8 over 3. Well, I have the derivative right here in terms of x and y. So y prime at -1/3 root 8 over 3 is, of course, -x, 1/3, over root 8 over 3, and that is 1 over root 8. Okay, well that's also 1 over 2 root 2, and if I wanted to rationalize the denominator, that could be root 2 over 4. So basically, that right there is the slope. Okay, now but it actually doesn't require us to do that, although it is kind of interesting to note that that is the slope right there. This is the answer that I'm looking for, at least for that first one. And what I need to do is basically I can either run through the same process that I did here and basically, use this point and this point and set it equal to this derivative, or I can just figure out where this derivative is actually equal to, where that derivative is equal to root 2 over 4. So, more than one way to figure that out. So the derivative of that second circle is 3 minus x over y. And of course that is root 2 over 4. You can, of course, solve the second one for its y equals, for that top half, because it's y squared plus x minus 3 squared is equal to 4. And therefore y is equal to 4 minus x minus 3 squared, but it's the top half of the semicircle. It's the top semicircle, the top half of the circle, so it's positive. And so I can get 3 minus x over the square root of 4 minus x minus 3 squared over, root 2 over 4. That becomes 12 minus 4x, and this becomes, root 2 times the square root of 4 minus x minus 3 squared. It might actually be easier to go ahead and keep it as x minus 4, because what I'm going to need to do is I'm going to need to square both sides, right, in order to free up that x that's under there so I can solve the equation. Remember, radical equations. This becomes 16 times x squared minus 6x plus 9. This becomes 2 times 4 minus x minus 3 squared. This becomes, this can become 8, and we can get rid of that 2, and this becomes 8x squared minus 48x plus 72. And this becomes 4 minus x squared minus 6x plus 9. And you would continue to work and work and work until such time as you basically get something that is solvable or factorable, okay? And so this winds up being negative x squared plus 6x minus 9 plus 4, so minus 5. This becomes 9x squared. I'm going to subtract 6x from the negative 48x. I'm going to get negative 54x, and I'm going to add 5 to this bad boy, and I'm going to get 77. Okay. I have, I'm continuing to toil along. So this is probably 3x and 3x, 7 and 11, if it factors, and therefore, okay. Well, you can always basically figure it out from that. But that's basically I'm not going to, elongate the video to actually do the arithmetic right here, but you get the idea. Basically, I like that problem because it folds in not just the calculus, but it folds in geometry and analytic geometry, and the only thing it doesn't really include is trig, right? And there are other ways to do this. I looked it up online, and there are just incredibly complicated ways to do it. But I wanted to show you this example largely because I think when we get past geometry and we start getting into Algebra 2 and Pre-Cal, we stop dealing with the shapes as shapes, and we stop, and therefore, because we're sort of out of practice in terms of geometry, it's not an instinct for us. We don't gravitate towards those things. I don't know. I hope you enjoyed that last one. It's kind of a neat problem, and it folds in geometry in a way that some of the other application problems don't. Stuff like one like that is not going to be on the test, but then of course I'm not teaching you to understand what's on the test. I'm trying to teach you math. And if you're able to follow along and you sort of were able to sort of appreciate what was going on there, that's kind of my main goal in that last question right there. But if you have any questions, please do shoot me an email, and I will talk to you then.